All right. So today, our goal is to study what we call frequency response and Bode plot. Right? This is going to be slightly different from what we have been doing so far. In which sense? So far, we were interested in what we call stability, right? Stability is somehow, the way we presented was a property of the system to asymptotically approach a solution given initial conditions, right? So the way you can imagine it is you start a little bit away from the solution, and as time goes on, you asymptotically approach it. Maybe with oscillations, maybe without oscillations, but you tend towards the solution. That was a stability. For linear systems with of the form x dot equals to ax, the solution is always x equal to 0 if the system is stable, if it is asymptotically stable. There is no other option. So the story becomes even simpler. It was always a question of, given initial conditions, how fast or whether or not you approach 0, right? That was so far the sense of what we were doing. Today, we are going to focus on a different aspect of behavior of the system. We are going to focus on how the system acts when there is an active input. In particular, today we are going to focus on the case when the input is a harmonic signal. So a sinusoid, potentially with a phase shift of arbitrary amplitude, right? So I have a system, there is an input, and we want to understand how it's going to work. But why is it important? Let me very quickly justify why this is of critical interest. So first of all, any type of systems that you actually want to control, you would probably want the system to do something. To do something usually means to travel from one instance of state space to another point on the state space. For example, for an airplane, it means to go from point where you start to the point where you want to land along a certain trajectory, right? It is always in motion, right? This motion would go along a trajectory. Now, arbitrary trajectories, just as arbitrary functions, tend to be extremely complicated objects. But a lot of simpler trajectories, a lot of simpler functions can be very easily represented as a sum of harmonic components. When I say this, I'm not trying to make a statement about, for example, theory of approximation of functions using Fourier transform or Fourier series. I could make this statement about Fourier series, Fourier transform, but that is not really what I care about when I make the statement. What I'm trying to say is your motions can be, roughly speaking, represented as sum of harmonic signals. And this is important because it is very easy to study how a system behaves when you have inputs which are harmonic signals. This ability to do it, to study how a system behaves, gives us a lot of information about how the system will behave when you do actual trajectory following. While it is very difficult to analyze how a system will behave on the actual trajectory, it is very simple to analyze how a system will behave given a harmonic input. That is the idea. And if you can make very strong statements about how a system will behave given a certain frequency of input, you'll be able to then hopefully make interesting observations about how a system is likely to behave on a trajectory. So that is the thing. We care about sinusoid inputs because it gives us information about everything else that we want to do, right? Not just because we somehow expect sine inputs to be in themselves a big part of our life, right? just the last part of motivation. If somehow this does not convince you, let me just give you an image of doing a pick and place. Let's say you have a robot that does pick and place, pick and place. This motion, if you imagine it repeated, looks like a sinusoid, right? You can describe the motion of my arm as a sine, right? Now think about other motions which you can describe as a sine, as a sum of two sines, the sum of three sines, with a shifted phase and everything else. There'll be quite a lot of them. So if it is difficult for you to go from abstract perspective to, like any arbitrary trajectory can be represented as a sum of sines, think about particular tasks that you can imagine as just being harmonic functions. A quadrotor filming a photo shoot. It flies around and the trajectory is just defined as a circle, which is sine along one axis, cosine along another axis. Something like this. All right. Hopefully, I convinced you that this is not a waste of time, but this is actually important. Now, let me show you what we're actually going to do with the lecture. All right. So first of all, let us understand a little bit better the signals. So I was talking about harmonic signals. That is input signal U of t. A harmonic signal is can be represented in this way: a sine times a amplitude of this sine plus cosine times amplitude of this cosine. Right? That is one way to represent arbitrary harmonic signal. A different way is to give amplitude and a phase. Right? Obviously, any harmonic signal would have to have a frequency. Right? Now, just in case, if you had the different frequencies here and here, it will be a sum of two different harmonic signals. A harmonic signal is still visually looks like a sine wave, right? So if you had two different frequencies, it would visually look like two different sine waves. So it would be a different signal. It wouldn't be the same. This hopefully is clear that this and this is literally the same signal. Now, how do you convert them from one form into another? Well, this M here is related to A and B like this. It is basically A squared plus B squared square root, right? So if you imagine this as coordinates on a R2 plane, this is a norm of this vector. Okay. And phase, this phi, is given as arctangent of B divided by A. In practice, of course, when I write arctangent, often enough, what I think of is arctangent 2. So be careful when you apply this. Like arctangent is more of a mathematical notation. Often enough, what we actually want, if we apply this in practice, is arctangent 2, right? So the arctangent that takes into account not just the ratio of B and A, but B separately and A separately as two inputs. All right, good. Well, this is a relation. This is just a background for how to represent harmonic signals. Now, we can do Laplace transforms of harmonic signals. So Laplace transform of a sine is given like this. It is omega, so sine of omega t. The Laplace transform is omega over s squared plus omega squared. Laplace transform of a cosine of omega t is s divided by s squared omega squared. So the difference between those two is in the numerator. Right? One numerator is omega, another numerator is s. Obviously, weighted sum of those two guys would be given by, would be given by omega times a, right? Here is this a. It happens, a times sine omega t gives you a omega plus bs. So b in front of cosine, s from numerator of the Laplace transform here. So that's what you have, right? This formula may look like it is, it was produced by taking some very clever integration by parts and so on. Like, sounds like it would be difficult calculus to produce this formula. But actually, this formula is just a linear combination of those two formulas. Those two formulas, how to produce them, that is a question that you have to take with the definition of Laplace transform, right? But having those two formulas, this final one is just a linear combination. Okay. Now we have seen basic ideas of what harmonic signal is. Let us try to do Laplace transform of this equation with a harmonic input. So we start with just considering ODE. Now we have this ODE with a n times y to n dot plus other components with less derivatives plus a1 y dot plus a0 y. That is the left-hand side. The right-hand side is given like this. Same thing, but now with u. And u, in our case, would be our harmonic input. In this case, I decided to give us a sine input. So notice it is not a generic harmonic signal, it is a sine. So I did not specify a phase. Could have been done, but I just decided not to. All right. So let us consider what's going to happen with the signal after we do the Laplace transform. So first of all, here what happens is quite clear. Every derivative will be replaced with the s to the power n, right? Same derivative, that was nth derivative, so it is nth power. Here's the first derivative, so first power of s. That is the 0th derivative, 0th power of s. So that's what we have. Same exact thing on the right-hand side, right? So far, quite clear. Now, let us see what's going to happen with u. So this equation, u of t equal to a times sine omega t. Well, we just learned that sine omega t gives us omega divided by s squared plus omega squared. And that's exactly what we have. Times a, so this a here becomes this a here. So very basic, very basic. But now what we can do is we can take this part, divide by it both sides of the equation. So we put it here. Thus we'll get a transfer function. We can take this guy, put it instead of u of s, right? And thus we'll get this transfer function here, right? Multiplied by this a omega s divided by s squared plus omega squared. That's what we have. The point of this exercise was to demonstrate to you that sinusoidal input appears in our transfer function representation on the right-hand side, multiplying the transfer function. Now, strictly speaking, equation 10 is not, at least I would not call it a transfer function representation. I would call it just a Laplace transform of a signal, because it does not transfer anything, right? It's not a transfer function. It does not transfer something into something. It's just a Laplace representation of a function, of a time function, right? Because input is already decided. But for me, what is important here is just how it appears here. So that's how it appears. That's how it does. If there are any questions, please ask. So because like we are going to move on, we are going to use this. So if something is unclear, please ask. All right. So now we set everything up, and we can start thinking about what is a frequency response. So frequency response is a steady state output of the system given a sine input, right? Here I could have, instead of sine input, I could have said harmonic input. I could have said a sum of sine and cosine input of the same frequency. All of this is roughly speaking the same thing. So I just gave a definition like this for simplicity, right? What does steady state here means? Well, given a sine input, your steady state solution is going to be also a harmonic signal. So steady state does not mean that the system, the state is constant. What it means is that it is periodic, but sort of like it is a periodic signal, right? As time goes to infinity, this periodic signal, like the signal tends to be more and more similar to strictly periodic signal, right? So steady in this definition, you can interpret it as it tends to be predictable. It tends to repeat itself. Just if a constant signal, every next point seems to be exactly the same as the previous point, in a steady-state response, given a harmonic input, your steady-state output is every output is the same over a period, right? So let's say you have a period of your signal, right? And given this period, you can expect that every point would just repeat itself after this period infinitely many times. That is the idea of a steady state here. Okay, all right. Now, let us consider this signal here, the system here. Y of s equal g of s times u of s. Right? If u in the time domain is a times sine of omega t, then in Laplace domain it is u is equal to a times omega divided by omega squared plus s squared, as we saw on the previous slide. So in general, what happens is if we want to study how the system reacts to sine input, we have to study this signal in Laplace domain. Y of s equals to j of s times a omega divided by omega squared plus s squared. Right? We saw it on the previous slide. The only difference is there we considered a particular differential equation here, right? And we showed that this is exactly what's going to happen. On this slide, I was not assuming any particular differential equation. I simply stated it as g of s multiplied by input. This is what we are going to get. In practice, this is the same thing because what we care about is systems represented by ordinary differential equations. So it is not a more general way of talking about things, but a different way to put it. Okay. All right. Now, what we would care to do now is to study how exactly system behaves given this sinusoidal input. So that's what we're going to try to do. Now, our tool for this study is going to be fractional expansion from the previous lecture. So in case it was clear, great. If it wasn't clear, right now is the best time to ask questions. I'm going to do this fractional expansion here. Make sure you understand what I'm doing. I will be happy to answer. All right. So what we're going to do is do fractional expansion on the system g of s equals to a omega divided by omega squared plus s squared. This fractional expansion, as I outlined in the last lecture, would have the following form. We would have r divided by s plus p1 plus r divided by s plus p2 plus rn divided by s plus pn. This has to do with the fractional expansion of g of s, right? That is what we're expanding here. Here, those p are poles, so roots of the polynomial in the denominator of g of s, right? That is what p are. Those r, r1, r2, rn are residuals, residue coefficients, you can say. Those are coefficients that appear because we apply fractional expansion, right? So they are being computed by performing this fractional expansion, right? Today I will show you how to compute, like the way to compute them, but a little bit fast. So okay, if you would have questions, you would be able to ask. All right, so those are residue coefficients. Now, final part is this guy here. This is the part of fractional expansion that has to do with the sign input. How can I justify this? Well, this times this would give us omega squared plus s squared. G here, J here is a complex number, the square root of -1, right? Complex one, I guess we can call it. So if we multiply those two together, we would get s squared plus j omega s minus j omega s. So those two cancel, and minus j squared omega squared. J squared gives us -1, minus times minus gives plus, so it will be omega squared. Those are just arbitrary functions that would have to be put there in order for this whole sum to be equivalent to this left-hand side, right? Okay, so that's how we're going to do the fraction expansion. Now, these guys here, they can be inverse Laplace transformed into this form, right? If you remember in the previous lecture, we showed that Laplace transform of functions of this type would have this form. In the last lecture, I think I showed you what happens when there's a minus here. Then there wouldn't be, in the formula, there wouldn't be minus there, right? I did this so P1, P2 would be exactly equal to the poles of the system, so to the eigenvalues. The way this is done here, P1, P2, P3, etc., would be equal to minus eigenvalues. So each of them would be same as eigenvalue or a pole of the system, but with a minus sign. But everything else is the same. All right, so each of those will be transformed into this form by inverse Laplace transform. Now, if the system is stable, and we are going to assume that g of s is stable, that means that all of those individual components of the solution are going to tend to 0. So in particular, it means that this minus pi together will give us a negative number. So pi would have to be positive. And this would mean that this contribution, 12, contribution of all of those components to the steady state solution is going to be 0. So they're going to disappear into 0. That is what we call a general solution. That is a part of the solution that has to do with how the system reacts to initial conditions. So these guys are going to tend to 0. All right. So as long as what we care about is a steady state response, what we care about is this part here. Since all of that would tend to 0 for a stable system, the only thing that is not going to tend to 0 is this guy, right? Now we have to be careful that we assume the system is stable. If we forget this assumption, we could accidentally try to perform all of those operations for an unstable system, and we may get the results which would not be nonsensical, right? We may, follow all the rest of the steps that I'm going to follow right now, and achieve some kind of, result, and try to work with this result. And it would simply be untrue. The assumption will be violated. So let us please remember, assumption here is that this component, this part of the decomposition, it has to be stable. So this has to go to 0, all of those components. This implies that P1, P2, P3, etc. are positive numbers, or simply that eigenvalues of your GS system are strictly negative, have strictly negative real parts, or whatever else. But the system G of S has to be stable. That is a necessary requirement to continue our decomposition, our work forward. All right. Hopefully that was clear. Now we can make next step. So our next step is to find these guys. So our next step is to find alpha of S and beta of S, right? That's what we're going to do next. To do this, what we're going to do is we're going to multiply the equation. So first we try to find alpha of S. We're going to multiply the equation by S plus J omega, right? S plus J omega. That's what we're going to do. So we're going to multiply everything by S times J omega. Just so you can clearly see it, let me go to the last slide. So imagine we multiply this component by S times J omega, S plus J omega. This by S plus J omega, this, and this. Everything is multiplied by S plus J omega. Notice that S plus J omega is exactly what is on the denominator in front of this coefficient that we are trying to find. That is the way to find those residue coefficients. All right. Okay. So we multiply everything by S plus times J omega. That's what we get, right? Alpha is now naked. It doesn't have a denominator because we multiplied by its denominator, right? I guess correctly, it would be correctly said that we divided through by its denominator. Okay. Now let us understand what's going to happen next. So first of all, let's look at this equation here. This guy is going to cancel this guy, right? So far, so good. That is all that's happening there. Everything else, we cannot really say anything so far. Now, to make a next step, we will consider S, which is equal to minus J omega. So we'll consider a case when S approaches or is equal to minus J omega. So this would allow us to make next steps. And next steps are quite interesting here. So first of all, this guy here, if S is equal to minus j omega, will become minus 2j omega, all right? Minus 2j omega. And we would be able to cancel omega in the numerator and denominator. So the entire expression will become j of minus j omega here times a here divided by 2 minus 2j here. All right, that is what happens in the left-hand side. On the right-hand side, things are even faster. S is here equal to minus j omega, right? Plus j omega. That means that this whole thing is cancelled. That is the trick that we're doing. Same here. S is equal to minus j omega plus j omega. This whole thing is cancelled. So our choice of S cancels this part, cancels this part. What we have is only alpha on the right-hand side and only this expression that I showed in 13 on the left-hand side. In essence, this is a method to find residue coefficients. We simply multiply everything by the denominator, divide through by denominator, how we call it. Then we allow the S to approach the root of this denominator so that everything that was multiplied by it will go to 0, except the coefficient in front of lambda and coefficient in front of the original system. And that is how we're going to do it. All right. All right. Next, we do the same with beta, right? So we're going to multiply everything by S minus j omega. All of the, then like this will disappear. Oh, let me show it carefully. This will disappear for the same reason, because we are going to allow S to go approach j omega, right? This will disappear. Here we'll have only beta left. And the only difference here is that we would have minus here, right? So it'll be S minus j omega. That's what we multiplied through. So this will go away, right? And S would be allowed to approach j omega. So we have 2j omega here. Omega will go away. And what we'll have is just, sorry, it will be just this guy here. A divided by 2j. So the only difference between those two expressions would be that here will be, the transfer function will be evaluated at j omega, not minus j omega. And denominator would not have a minus here in the second case. That's it. That is it. So while all of this may look sort of, like we are doing serious math here, actually what we do is quite mechanical. It's not very complicated. So, multiply by number, cancel everything that goes to 0, substitute minus j omega instead of S, cancel everything that cancels, you get the expression. So it's not complicated. That is, I think, the main takeout of what I'm showing you right now. Okay, next. So we have our steady state solution having this transfer function, this Laplace representation is alpha of S divided by S plus j omega plus beta of S divided by S minus j omega, right? That is Laplace representation of our steady state solution. Okay. Now we can find inverse Laplace transform, and since we since we know that alpha of S gives us A divided by let me be careful that yeah. Since we know that beta of S gives us Laplace transform that is equal to A divided by 2GS times G of J omega times this guy, right? Since we know that alpha of S gives us G of minus J omega minus sine still A divided by 2 J, right? And then there is this guy, right, from here. We can just expand this into 16. So 16 is simply like this equation. We substitute alpha and substitute beta, put this guy out of the brackets. That is all that we've done. Okay. Now we can try to find inverse Laplace transform of this thing. Now, this is simply a coefficient. It can go in front of the Laplace transform. This is also a coefficient. You can see it doesn't have S inside it, so it also goes in front of the Laplace transform, right? What we're actually going to transform is this function and this function. Well, the first one gives us Laplace transform in the form exponent. Let me be careful here. It gives us exponent to the power of this coefficient. So exponent to the power of this coefficient. Second one gives us exponent to the power minus this coefficient. Why there is a difference between first and second? Because of the sign, right? If there's a minus sign here, you don't need to put minus in front of exponent. If there's plus, you have to put a minus here. Right? Everything else is, as you can see, just goes directly from Laplace transform to the time domain without any change. Like this is transferred without any change. This is transferred without any change. This is transferred without any change. All right. So hopefully you see how we arrived to 17. Just took inverse Laplace transform, which requires a simple table transformation from the last lecture. All right, good. Now a little bit of a few facts from theory of a function of a complex variable, right? So first of all, a complex function can be represented in a polar form. In the polar form, a function looks like this. So omega of x is a complex function. In the polar form, it is represented as r of x, which is a real valued function. This would be called amplitude, times exponent to the power theta of x times I, where theta of x is a phase. So this is amplitude, this is phase, right? That is what does it mean? Hopefully you had you remember a little bit of theory of complex variable. But if a rational function, a real function, you can say a rational function, it maps you to the real line, right? To the real line. Complex function maps you to a point on the complex plane. Let's say here. So given any input, it maps you somewhere on the complex plane. So what happens is your function can be represented in two ways. One is by projecting it on a real part of the complex plane and on the imaginary part of the complex plane, right? And this would be like Cartesian representation of the complex number. Or you can alternatively just say, how big is this vector? And what is the orientation of this vector? So, and this will be sufficient. That will be equivalent to the first. Those two representations are the same thing, right? So here, polar representation, that is the second type. where you ask how big is the number and what it is its orientation. Okay. Now, relations between Cartesian representation here and polar representation here is like this. R of x is absolute value of omega of x. We'll call it amplitude. In particular, how do you compute it? Just square of the real part plus square of the imaginary part, square root. Right? Phase, here we can call it a phase of omega of x, is computed by taking arctangent of imaginary part divided by real part, or arctan of imaginary part, comma real part. Right? So we can easily go from polar to Cartesian, or from Cartesian to polar. And in particular, if you want to go from Cartesian to polar, this is the equations that you need. That is factoid number one. Factoid number two. The size of a vector produced by a complex function would not change if your complex variable went from being jx to being minus jx. J, remember, is J is your imaginary one. Okay. So this transformation would not change your amplitude. On the other hand, this transformation will change your phase to the opposite. So your phase would change from positive to negative, or from negative to positive under this change. If you replace your variable from minus jx to jx, your phase would change sign. So, yeah. Factoid number two. Okay. Now, factoid number three. Sine of x can be represented as e to the power ix minus e to the power minus ix divided by 2I. This, if you remember, this happens to be Euler identity. I think you can derive it quite easily from there, I believe. But there is like multiple ways to derive this. But yeah, okay. I'll avoid talking about this. But if you're interested, and if this strikes you as unusual, that is a perfect way to spend an evening trying to prove this formula. It's one of those formulas which is easy to prove with your level of calculus, and it's like one of those beautiful things about calculus and complex variables. Like it's just pleasant to work with this type of formulas. So I recommend, if you are thinking how to spend an evening, you can spend them proving these formulas. All right, good. So those three factoids, we'll use them in the rest of the proof. So hopefully we got them. Yeah, move on. Now, g of x, I would replace it with r of omega, oh, sorry, g of j omega. I would replace it with r of omega times exponent of theta of omega j. G of minus j omega, I would replace it with r omega. Notice the same r omega, because minus sign does not in here, as we said, does not influence the amplitude, right? And minus theta omega, so the phase changed sign, right? So you can see the second factoid, we used both first and second factoid already. We changed into polar form, and we noticed that the sign of the amplitude will the sign of the phase will change, amplitude will stay the same. All right, r of omega here is a absolute value of g of j omega. So the amplitude, right? This phase will be computed like this. Okay, good. Now, you remember this was our steady state solution in time domain. What we are going to do now is replace, let me be careful. So we'll replace this with this, right? And we'll replace this with this. That's it. That's it. Now, next step, we'll observe that multiple of two exponents is just one exponent with the exponential values summed, right? So that is the next observation. We also put this guy out of the brackets because there's a common factor, right? It goes here. And now we use the last factoid that we invoked in the slide, namely that exponent to imaginary 1 times a real number minus exponent to the imaginary, so this is imaginary 1 times real number divided by 2 imaginary ones, right, is just a sign. So that's the last one. So all of this becomes just a sign. And this guy in the brackets, that is just what we had here in the exponent. That's all. That's all. Notice, obviously, the imaginary part here goes away, this imaginary part, because of how the formula is set up. You remember, in the formula, it was exponent to ix minus exponent of 2 minus ix divided by 2I. That is the sign of x. So those imaginary ones go away. All right. Was complicated. I'm sure that was complicated. I'm sure some of you might feel like it was difficult. And for good reason. We used a lot of information here, right, so far. And it, required quite a few slides. But what did we get? Well, what we got is this expression for steady-state solution. Now let us look very careful there. This expression has A, which is the amplitude of the original signal, times R of omega, times the sine wave, which is shifted by phase theta. So now we know what's going to happen with our system. If we put sine wave with amplitude A, what we're going to have is amplitude change governed by R, which is just the absolute value of the transfer function evaluated at j omega. And it is going to have a phase shift, which is just the phase of this transfer function evaluated at j omega. Notice that both the amplitude change and the phase shift depend on the frequency of the input signal. So some of the frequencies would have big amplitude change, some would have small amplitude change, some would have big phase shift, some would have small phase shift. That depends on the amplitude. Oh, sorry, on the frequency. It's not the same for all frequencies. And that is an important fact. But yeah, that's what we were able to do with this whole thing. Right? So if we care about amplification of sine signals, the amplification is the ratio of this amplitude to the original amplitude. And it's just Rn, R of omega, this is just absolute value of the transfer function. If we care about phase shift, it's just theta of omega, it's just this arctangent here. Now, we did make a few steps. Steps were complicated, right? First, we put everything into Laplace domain, did fractional expansion, calculated alpha and beta coefficients of fraction expansion, then put those coefficients in front of, like, formed with them steady state solution, Laplace image of a steady state solution, did inverse Laplace transformation into time domain. Then we used quite a little bit of function of complex variable stuff to put it in a polar form, and then in this like sine of omega t plus theta form, right? Quite a few steps, but those are not crazy steps. Like nothing that we did was math that you know out of your pay grade, right? You can perform all those steps. That is important. I want you to keep this in mind. Like it was not the type of proof that is impossible to follow, impossible to verify. It is a normal, doable proof. Okay, now let us understand what we can do with this. So what we can do with this is, for example, plot a Bode plot, right? Bode plot is a plot which consists of plotting amplitude amplification in decibels. So to plot something in decibels, you take a log of it, multiplied by 20, right? That's what we have. And 20 has to do with the fact that people who were inventing this type of notation back in the days cared about energy and like energy of the signal, original of the signal. So 2 would have something to do with power of 2, right? Energy tends to be like a square of a signal. And a 10 has to do with decibels, deci, right? 1/10. And here to plot phase, you just transfer your radians into degrees. That's classical, traditional form of a Bode plot, right? Why do we care? Why do we care about Bode plot? Why do we care about any of this? Let me show you. First, I'll skip this example. If you want, we have in the slides example of how to do it by hand, but I'll just skip it. I think we had enough math for now. But for self-study, go ahead and use it. For now, I will just go straight into an example of a Bode plot. Let me even go like to this example here. Right? Then I will return and we'll go through the rest of the slides. Okay, so this is an example of a Bode plot. Right? This plot here is the plot of amplification. So how much the amplitude of the signal is going to change based on the frequency. So this axis is frequency, this axis is amplification, right? This is a phase shift. So this shows in the vertical axis by how much the phase of the signal is shifted. This shows against frequency, right? Now, let's say you want to ask yourself, I'm going to put sine wave through my system. What am I going to get on the outside? Well, in this particular example, if your sine wave is very, very, very low frequency, like here we're talking about 1/1000, almost like here, 1/1000 radians per second. So your sine wave is almost imperceptibly moving, almost imperceptibly, right? It's almost just a steady input which slowly shifts. Well, your amplification is going to be 10 to the power 0, which is 1. So your signal is actually not going to be amplified at all. So you can expect the output will be exact same sinusoid as your input in terms of amplitude. Now, what is going to be the phase shift? Why do you care about it? Well, phase shift is how much you lag behind. You send input, do this, your system does instead this, right? Like you wanted this, go up and down. Your system does this, go down and up. That's like 90-degree phase shift. Well, the shift here is zero. Seems to be straight zero, right? So no phase shift at all. So you can imagine this system seems to be doing perfectly fine on low frequencies. It is going to amplify your signal not at all. What you put on the input, you're going to get on the output, right? And there is no lag of time on this, at least those frequencies. Okay, good, good. Now, there seems to be something strange going on around frequency of 1. So frequency of 1 is here. And here you can see it starts to rise. It rises, rises, rises. And this may mislead you into thinking that here it arrives at a peak of y equal to 360. In fact, it doesn't mean anything. With those tools that are based on numerical calculations, needle-like peaks like this are impossible to compute because you will compute like left of the peak or right of the peak. So this is actually infinitely high peak. So what this demonstrates and that is that this system would have a resonance frequency. So at around this peak, it's going to blow up to infinity. All of you probably have heard of like bridges that collapse because of the resonance achieved by people who like march in like in the same frequency as eigenfrequency of the bridge, and it just collapses, right? Probably you yourself try to like oscillate something with a frequency that actually seems to be like, inputting more energy into the system that the systems can dissipate, right? It's a common experience. It's a common experience. So this system appears to have this frequency, which if you work on this frequency, it is going to your signal will be amplified. And it is not just this frequency; it happens to be a frequency of 1 for the system. A lot of frequencies that are close to 1 also produce gigantic amplification, which you don't want to have, possibly, right? Imagine you put a small sinusoid signal in, you get gigantic sine out. Do you want it? Maybe not, right? All right, good enough. But what happens after? Well, after this frequency here, you can see that the output frequency tends to go down and down and down and down. The higher you go, the lower the output. And look at those numbers. Like this is 1 over 100. This is 1 over 10,000. This is 1 over a million. What you can clearly see is that the system will be able to track your input worse and worse and worse as the frequency increases. So you can reasonably say that after a certain frequency here, the system is not suitable for work. You cannot work with this system with frequencies that are higher than something here. Because either you go into resonance or the amplification will go smaller and smaller and smaller and smaller. You won't be able to track. Like you ask the system to oscillate very fast, it's going to oscillate, but it is going to barely be perceptible. It's going to stand in place, right? Okay, good analysis, good analysis. And also you can notice that after this frequency here, you would acquire a phase shift of 180 degrees. So your system would oscillate, but it will oscillate with a lag of half a period. Questionable behavior. I'm not saying that you cannot work with it. Like there are plenty of cases where resonance is useful, plenty of cases where unstable behavior is useful. I'm just saying that it is important to be able to tell that this is how your system is going to behave. And that is achieved with Bode plot. Like this is an example of a Bode plot. Are there any questions so far? Any questions so far? Oh, my apologies. Did I take, I think I took a little bit too long. No, we are out of time, right? Okay, someone tell me.
No, we have 30 minutes.
30 minutes. Okay, good, good, good. Sorry about that. I panicked a little bit. Okay, all right. Good. So we still have time. One moment. All right. Any questions about this? No? Then I will go back and I will show you what is considered to be a classical use case for Bode plot. What I'm going to show you right now is what you're going to see in, I think, more or less any textbook with respect to how to use Bode plot. Right? What I think it is important for you to understand exactly what this textbook tells you. It's like it is bad to have oversimplified picture of what I'm going to tell you, right? So let's try to understand details. So classical use case for the Bode plot goes like this. You remember if we had a simple feedback control, so basically we take output of the system, multiply it by a controller, then we put it as input to the system with a minus sign. So that is what we call a simple closed loop feedback control. Just output of the system, multiply by controller, times -1, put as input to the system. This is a transfer function that we're going to get. This is a transfer function that we're going to get. If you want to like explicitly to put controller in this picture, it will be here, right? The controller will be here. Now let's assume the controller is equal to 1, right? So controller is just like doing nothing. So you just take your output of your system, multiply by -1, put it as input to your system, right? That is the picture exactly now, what we're going to get. What we can do next is we can perform our standard Bode plot. For that, let us go back 2 slides. What we do is we replace our variable, which is, has real part and imaginary part, with only imaginary variable. So sometimes we say we go from Laplace domain to frequency domain. Because sometimes you hear this kind of stuff. So we replace S variable, Laplace variable, with a frequency variable, J omega, right? And you compute your amplitude, as we said, by finding absolute value, and your phase using arctangent tool. Right? Good. So that's what we're going to do. We replace our S variable here with J omega here, same here, right? And we get our transfer function, but now in the frequency domain, in the frequency variable. Let us notice that this fraction is going to be ill-defined if ever this transfer function achieves a value -1. This is a big problem. If it is -1 at any point, then this fraction blows up to infinity. Not a good sign. When is this going to happen? Oh, when the amplitude of G of J omega is equal to 1. So when amplitude is equal to 1, so amplification of the input signal is equal to 1. Second requirement is for the phase to be 180. So a -1, just x minus x equal to -1. This can be seen in polar coordinates as amplitude 1, phase 180 degrees, right? I understand that this is a little bit strange to think of real numbers in terms of amplitude and phase, but you can, right? There's nothing wrong with it. So positive numbers would have a phase 0, negative numbers would have phase 180, right? So -1 is phase 180 and amplitude 1. And that is what we want to avoid. If we ever see our G of J omega becoming amplitude 1, phase 180, that is when this closed loop will blow up. That is a big problem. let us try to understand when it's going to happen and how we work with it. So here comes the idea of margins. So here is a picture of a Bode diagram. You can see here is a magnitude, here is a phase, right? Magnitude and a phase. Now, here's the magnitude plot. It is 20 decibels here, minus 20 decibels here, and linear in between, right? By the way, those linear plots, those plots with sharp angles, usually are achieved by plotting a Bode diagram by hand. There's entire art of how to do it by hand. You don't have to use computer, but I'm not going to teach it to you. But the plotting Bode by hand takes way more time than to do it by computer. I don't see a reason why in such short introductory course you need to know this. But be aware that in a big textbook or in a longer course, especially more classical course, you'll definitely find quite a lot of information related to how to plot it by hand. That is what used to be done the whole 20th century when people were doing control theory. Right? Computers made it easier, but that was a classical thing. And those sharp Bode plots usually are plotted by hand. All right, so 0 decibels is when you have your amplification of 1. Right? The 0 decibels is when you have your amplification of 1. So this is a point right here. Let me put it in red, where we achieve amplification of 1. And remember, what we are afraid of is amplification of 1 and phase minus 180. 180 is what we are afraid of. All right. So this is one point where one of those conditions is already happened. Now, at the same frequency here, we have a phase which is not 180, right? Not 180. The phase here is 189. All right, so at least we're not there. At least we're not there. Okay, good. That is not all the information that we can get from it. What we can get from it is the fact that we are only 9 degrees away from crossing this line, from arriving at this 1 amplitude, 180 phase. So this distance is what we call phase margin, right? That is how far we are from crossing this boundary. The idea of a phase margin is that your controller will affect your phase. If it affects it in such a way as to push you 9 degrees forward, you can expect your phase, right? You can expect you would cross this boundary and you get unstable system. You would have this explosive resonant frequency, something like that. Basically, your closed loop system will become unstable. Okay. We can do the same for gain, so for amplitude. Let us look at this. So here at this point, we arrived at 180 phase, right? So we are at this dangerous point when the phase is 180. Thankfully, at this very point, the gain is 20 decibels, right? 20 decibels. If it was 0 decibels, we would have been in big trouble. But we're not, because it is 20 decibels. So we call this 20 decibels a gain margin. Right? So we can, if our controller decreases our amplification by 20 decibels, then we'll be in trouble. But until then, we are fine. That is the idea of margins. And that is the thing, right? That is the thing. So there is a lot of terminology, as you can see, for example, on this slide, we have gain crossover frequency. So what is the gain crossover frequency? It is a frequency around which you cross this 0 decibel amplification. What's the phase crossover frequency? That's a frequency around which you cross 180 phase shift. Good. What I think is quite critical to understand is this analysis deals with a simple feedback loop. So it deals with a controller that is a modification of this simple feedback, right? It talks about what will happen if you put here a controller, which would modify your phase, modify your amplitude, right? Amplitude amplification. But we need to understand that when you put this controller there, you also need to be careful that you don't break your stability, right? Like remember what I said here when we were talking earlier. Let's see if it allow me. Okay. When we were discussing this slide, I told you, I think maybe even this slide will it allow me to go. Yeah, this slide, right? We were talking that those components have to go to 0 because the system has to be stable. If during your Bode analysis or whatever, you get a controller which actually breaks this condition, the whole plot becomes invalid, right? So you have to be careful. It's very easy to look at this plot and forget the assumptions while you are excited about changing your controller and tuning it and so on and so forth. Also, I see quite often people don't use this analysis right now to tune a controller because controller is tuned by pole placement or by LQR or anything else. We will learn a little bit of this during this course. But what I'm trying to say, it is not tuned by hand as often, at least, for people who do it as part of the study, as part of simple research, and so on. So people tend to forget about Bode diagram altogether because they're not using the gain margin, phase margin in their part of the control design. They don't care about it, so people forget about the existence of Bode plot and becomes somehow ignored. That is not a great idea because Bode plot, even if you are not going to use it for your gain margins and phase margins, especially since you have this very convenient eigenanalysis and so on, it is very useful to understand your response in terms of amplitude and phase to the signal. Even if you're not going to use it for design, you have to use it's very good to use it for analysis of your behavior. Right? So let me give you a simple example here. Let me see. I still have a little bit of time. So here we have a system. This system, I specifically chose it to have a resonance. Eigenvalues of the system are plus minus imaginary one, right? So plus minus j. A resonance frequency of the system is omega equal to 1. There is a whole separate sort of like field of study called like study of oscillations, study of resonance, where there are formulas, especially for systems of the second order, where you can explicitly find resonance frequencies. And it's not complicated. So if you are interested, it is not difficult to find this type of analysis. But in any case, in this case, the resonance frequency is 1. Now, if I do a simple feedback, so I put my output y equals to cx as my input y with a minus sign here, right? What will happen is I would have ax minus b times cx. So a minus bc would be my new closed loop system. The eigenvalues of this new closed loop system is plus or minus square root of j. The resonance frequency of this new system is square root of 2. Okay. So that is just an example. I did all this analysis sort of like not on the slide, but somehow, by myself. I'm not showing you how I computed those frequencies or eigenvalues, but you can trust me that this is what happens. Now let's look at the Bode plot of this system. That is what I showed you earlier. So I said that resonance frequency is 1. That is exactly what we see here. There is a spike that would go all the way to infinity, and the height of the spike depends only on how fine the resolution is. If I manage to hit exactly 1 on my grid search here, I would have managed to maybe break the Bode calculator in MATLAB, or depending on how it is computed, produce numerically strange result. Like correct is infinity. Correct result is infinity at this point. All right. So we can see that there is this gigantic spike. After the spike, as I said, the system tends to act as a low pass filter, right? It allows, hopefully I'm not mistaking this terminology here, it allows all the signals with a low frequency to pass unchanged, but high frequencies are attenuated, and the higher the frequency, the higher is attenuation. Notice that this is a log axis, so this is more or less exponential. I don't want to, I guess I don't want to stress that it is exponential because both axes are log, but the attenuation is fast. That's, I think, is important takeout. Attenuation is fast. Okay, good. Now let us see this point. This point is where we have our attenuation, our amplitude amplification to be equal to 1. So it is what we call this frequency here is what we call a gain. Let me look up the term so I don't mangle it. Okay, gain crossover frequency, right? Gain crossover frequency. That frequency is what we call gain crossover frequency. Good. Notice it is the square root of 2. 1.4, 1, etc. This is the square root of 2. This might not look exactly like square root of 2 because I put the point not exactly at the gain crossover frequency, but as close as I could. As I said, this is a tracing, like we do like grid search over those numbers, you can see, and we don't hit exactly the frequency. Right, you can see this 0.98 instead of 1. That is why this is not exactly square root of 2. Okay, so this is the frequency that we care about. This line here is a line where amplification is equal to 1. Now, at this frequency, you can notice here the phase is minus 180. So we are going to get our promised problem. The problem would be, as we said, closed loop system will blow up. Now let us go back slide and let's look at this closed loop system. Well, in fact, in this frequency is a resonance frequency for this system. And notice eigenvalues happen to also have this square root of 2. And here there's 1 also in the eigenvalues. So Bode does help you identify those resonances. But I think, like, in case you find this whole business with gain margins and phase margins a little bit not to your taste, I know somehow a lot of people who, especially who do research now in state space form and so on, they don't automatically go to Bode plot whenever they encounter a new system. Somehow it just doesn't happen. No one says anything bad about Bode, but I don't see people use Bode plot as often. Let's say you feel strange about margins. Well, you don't have to use it for margins. You don't have to use it to compute your phase margins and gain margins. You can simply use it to see directly resonances like this. If I plotted this same plot, but for the closed loop system, it would have a resonance frequency. It would be here. And it would be visible, perfectly visible on the Bode plot. So in case you don't want to use Bode plot to analyze simple closed loop system, which sounds maybe for you a little bit too complicated, especially since maybe you're not using simple feedback. Maybe you are studying already a closed loop system, for example. Well, don't just look directly at questions of amplification, like how much amplification do you achieve at different frequencies. Look at the phase shift. That's going to tell you how your system will behave, how much lag you are going to have between your input and your output. If you're, for example, designing a system which traces the hand of a person, let's say for writing, or maybe for surgery, lag is going to be a big factor in your system. You're going to care a lot about lag. If, for example, if the person looks at what the robot does and wants to correct it, lag of 180 degrees might be critical because the robot will, if your person does a sinusoidal movements, your robot will go up when the person goes down, That is not an insignificant aspect of a system. So even if you are not going to use Bode plot for control design, still use it for analysis. It's a very useful tool. All right. I think I'm done with trying to advocate for Bode plot. As usual, we have this information in the textbook. Here you can use this chapter to learn more about Bode plots, and some of the derivations you can see there as well. This excellent lecture notes, they're same as the slides, but different perspective, different lecture, and so on. Very well done. So in case in my slides maybe something is not clear, you can go through these slides for this lecture. Very high quality, very good. Some video explanation of the same thing, right? Another notes for the same thing. If you are interested also at the end of this lecture, I put a little bit of suggestion of the connection between Fourier series, Fourier transform, and Laplace transform. If any of you are studying right now signals, and I'm not sure if you have this course in your curriculum. In the past, it was happening at the same time as control theory, but I'm not sure if this year it also happens. You can find the similarity between Fourier transform, Laplace transform, even visual. You can see that the transforms themselves are very similar. And you can notice that the difference between them is the fact that here the complex variable has only complex part. Here the complex variable has complex and real part. This difference somehow seems to go away when you replace your your complex variable sigma plus j omega with just j omega, right? So it seems like Fourier transform has a natural connection to Bode plot, and it makes sense. Fourier transform is about representing a signal in terms of sum of harmonic signals, and that's exactly what we are doing with our steady-state solution. Well, that was just for if you want to think about it, trying to build intuition about what happens here. All right, I think that is it. Do we have any questions?